Welcome back. We're looking at section 4.8 today. It is about antiderivatives. And as we've spent this far in calculus learning about derivatives, how to take derivatives, how to use derivatives, as an operator, it must have a inverse operation essentially, right? Like multiplication has division. They're the same thing, just in different directions. Addition has subtraction, same thing in different directions. Squaring something and the square root of it, same thing in different directions. Those are all operators and they all have inverses, and likewise, derivatives do too, and we call them antiderivatives. We're going to talk about the power rule specifically for derivatives. So if you remember what the power rule, the derivative of x to the n with respect to x is equal to, we bring down the n, multiply it by the front, and subtract 1 from what it became. So example would be, what's the derivative of 3x squared? So the derivative of 3x squared, we bring down the 2, times it by the 3, and that gives us a 6x, and subtract 1 from the power. So we're left with 6x. Well, the antiderivative power rule is a little bit different, okay? So when you see this symbol, so you've got some function of x with this little large s curve and a dx, so those are the symbols, right? So instead of d dx, which is what we used for derivatives, for antiderivatives we use this large s curve and a dx, and it's sandwiching the function that we're operating on inside of it. And so we want to essentially have an operation that's going to turn 6x into 3x squared. That's going to be our antiderivative because it undoes the derivative. So, turns out how you do that is the antiderivative of x to the n, instead of subtracting 1 from the power, we add 1 to the power, and we divide by what the power became. And so, to put that through the ropes, let's take 6x. So the antiderivative of 6x with respect to x, or dx. Okay, so we add 1 to the power, x to the n plus 1. 1 plus 1 is 2, so now we have x to the 2, right? We add 1 to the power, x to the 2, and then divide by what the power became. And so we have 6x to the 2 divided by what the power became, which is 2. So in other words, n was 1, right? So 6x to the 1, we added 1 to the power, that's x to the 2, and we divide by what it became, and that's also 2. And just like with derivatives, antiderivatives are linear as well. So they are linear operators, which means that we can actually pull the 6 out front, we can pull constants out, and we can multiply them back in later. Similar with derivatives, linearity also applies, and so for example, if you wanted to take the antiderivative of a function 3x squared plus x, you can write this, just like you could split a derivative, you can write this as 2 antiderivatives, like this. So, just like with derivatives, pretty much anything you can do with derivatives because of linearity, you can also do with antiderivatives. A few things to remember: it's very easy to do them backwards. So in other words, you'll find yourself needing to take an antiderivative and you're going to accidentally take a derivative. And it's very common. It still happens to me. Of course, these symbols are wildly different, so just pay attention to the symbols and ask yourself every time, am I taking an antiderivative or am I taking a derivative? Yeah, anyways, that counts as the 3. So we get back our 3x squared. You might ask, well, this is the power rule. What about the chain rule and the quotient rule and the product rule and all those sorts of rules? Rules of logs, rules of, inverse trig functions. And the thing is this course, Calc 1, it introduces the antiderivative, but it doesn't explore all the methods to solve it, because solving antiderivatives tends to be much more difficult than solving derivatives, and it requires its own set of tools that do things backwards, essentially. Pretty much anything somebody can hand you, you can take the derivative of. pretty much any function anybody could ever hand you, you can take the derivative of. But 99% of antiderivatives are unsolvable, and we have to end up solving them using estimations, approximations, and so it tends to be a much more challenging game with the antiderivative. I hope this was helpful. I'm going to do a video about how these two geometrically relate to each other, and I'll post that soon. Thanks for watching, and I'll see you next time.